Okay. So I'm Alexis Reboul-Salze. I'm a postdoc at the Max Planck Institute for Gravitational Physics in Potsdam. Sorry, it's not. Is it working now? Yeah, perfect. So yeah, I'd like to thank the organizer for the great workshop, and we had some very nice overview talk about binary neutron star merger in short and long GRB. But I'm going to talk more specifically at what happens really inside the neutron star remnant when you merge, and how the magnetic field is amplified in this case, and what are the implications for observation. So first, the motivation to look at how the magnetic field is amplified through dynamo process is to explain how do we form jets for GRB. And we have now many simulation, first principle simulation, that showed that if you have a strong and large scale magnetic field, then and a compact object that is spinning rapidly, either a black hole or hypermassive neutron star or millisecond magnetar, depending on which scenario you're looking at, then you can form some jet, some relativistic jet, as it was also showed by Daniel in the previous talk. But if we take a look at binary neutron star, the neutron star are quite old, so there's no reason to have already a very strong magnetic field of a few 10 to the 15 Gauss. It would be more 10 to the 11 or something closer. So this is why we need to look at what kind of mechanism can amplify the magnetic field so we can reach the one needed to form a relativistic jets. So there's different phases of the binary neutron star where you can have different instabilities. So you have the in-spiral where there could be some tidal effects and some resonance there, but I'm not going to speak about that today. I'm going to focus more about what happens right after merger, so the Kelvin-Helmholtz instability, where you create a shear layer between the two neutron stars that will be able to amplify the magnetic field. And then in the second phase, when you have a remnant, which is in differential rotation, so you can have some winding, and you can have two different types of dynamos happening in this remnant. You can have the Taylor-Sprague dynamo, which has been studied for mainly stellar evolution and forming magnetar recently, and the magnetorotational instability. It has been studied a lot for accretion disk physics. So the first instability is the Kelvin-Helmholtz instability. And you can see here the shear layer between the two neutron stars that you can amplify the magnetic field. The initial magnetic field was around 10 to the 11 Gauss, and you can reach 10 to the 16 Gauss. But as you can see here, it's a small scale magnetic field. So it's not the type of magnetic field that can explain the formation of a relativistic jet. So the question is how from this small scale magnetic field, strong but small scale magnetic field, how do we get to the large scale magnetic field? And this is the initial condition that you have right after merger. So after the Kelvin-Helmholtz instability sets in. So you have here a magnetic spectrum. You can see that it's over many different scales, and the magnetic field is stronger at small scales. And here is the rotation of the remnant, of the hypermassive remnant at different time after merger. So this is coming for a very high resolution GRMHD simulation with the DD2 equation of state and 1.35 equal mass binary. And you can see you have two different regions for the two instabilities, the Taylor-Sprague dynamo and the MRI. Which are separated depending on the sign of the differential rotation. If your rotation is decreasing, then you will be unstable to the magnetorotational instability. And if you have an increasing differential rotation, you could be unstable to the Taylor-Sprague dynamo. So let's dive into each dynamo separately. And we'll first talk about the magnetorotational instability because this happened on the outer layer. So it will be more connecting to the ejecta and the jet. And here are some, I'm reminding some properties of the MRI. So the instability criterion is that you need to have negative differential rotation. It has a very fast growth rate that depends on the rotation. So a few milliseconds growth rate for hypermassive neutron star. But one difficulty to simulate this instability is that its wavelength is proportional to the magnetic field, meaning that if you want to resolve it in global simulation for merger, you need to, unfortunately, start with a strong magnetic field, or you need to study it in local model. There you can start with a lower magnetic field. And this instability will drive turbulence, then can have two different impacts. So you will have some angular momentum transport due to the turbulence, mainly due to the small scale turbulence. And we can look at what happens on the large scale magnetic field. So if you average, for example, in the azimuthal direction, the induction equation, then you can see that you have the average quantities, magnetic field velocity, that can generate the field. And you can have a contribution from the very small scale, some nonlinear contribution from the small scale that for some models has been shown of the MRI that can be linked to the average magnetic field, and that form a cyclic dynamo that we call an MRI alpha omega driven dynamo. And this is exactly what we see that happen in the GRMHD simulation. Here it's so what we call some butterfly diagram. So at 30 kilometers, we look at the average magnetic field. So you have the toroidal here, and you see some cyclic behavior, some oscillation with a 20 millisecond period. And you can see the two different loops for the magnetic field amplification. So you have the winding by the differential rotation. So this shows that you have anti-correlation between the radial magnetic field and the toroidal magnetic field. And you can see also the nonlinear effect here, which is proportional again to, which is correlated with the toroidal magnetic field. You can see similar batches of patch from the small scale contribution. And this is what regenerates the poloidal field and completes your dynamo loop. And we can look at the propagation of this magnetic field because here we were showing the vertical propagation, but it's also some radial propagation. And we can actually make the link directly between the polar outflow, between the relativistic jet and the alpha omega dynamo. As you can see here, propagating radially towards the polar region at like 10 kilometers. And it's really the equation, the propagation of this magnetic field is what launches the jet in this simulation. And this is typical magnetic field line turbulence. And you see the radial field lines that goes towards the top and generate the poloidal outflow. And on the more equatorial plane, you have some turbulence there. And the jet that we find strong luminosity, 10 to the 52 erg per second, concentrated in a 10 degrees angle with magnetization parameter quite high for this kind of simulation, around 10, even 20 sometimes. And the MHD, the MRI-driven turbulence also generate, as was talked by Daniel, some post-merger ejecta to the winds of the accretion disk as well. What is quite interesting is that we can also look at this oscillation of the dynamo frequency, and we can find it again in the Poynting fluximeter, so in the jet luminosity. If we look at 500 kilometers from the central object, we can actually see in the spectrograms some lines that correspond to the dynamo frequency that we have at very close to the remnants. So it's a clear evidence to show that it's really the dynamo process that impacts the jet luminosity directly. And since we have different dynamo frequency depending on the type of compact object, I mean, we can maybe learn more about the repartition of the mass of the central object and also some disk properties if we do some theoretical scaling for the alpha omega dynamo frequency. So this could be a very interesting point to see what is the central engine, because we would expect for black holes to have a lower frequency than for a neutron star remnant. Of course, this has many caveats because it's really close to the central engine. and you have the jet propagation, and many things can happen on the process, and doesn't mean that the variability that we find here can really be found in the prompt emission of the GRB. It's still quite interesting. We also need to learn more about the MHD process in itself, because some parameters that are very important for the MRI is the magnetic Prandtl number. So it's the ratio of viscosity in the fluid over resistivity. And this parameter, both for hypermassive neutron star and for the inner part of the accretion disk, is very high. And in local simulation, we have found that when you increase this parameter, you increase the angular momentum transport. But not only the angular momentum transport, you also increase this dynamo, the efficiency of the dynamo for the large scale, which is through this dynamo coefficient, the alpha dynamo coefficient, which is much 3 times larger in local simulation compared to the global GMHD simulation, where we take into account the viscosity and resistivity. This means that we could have a magnetic field which is more than 3 times higher than what we found in the GRMHD simulation, which then could mean that we have higher luminosity, higher magnetization parameter. Also, the winds driven by the magnetic field could be stronger as well. So this is really a new regime for the magnetic field that needs to be studied and the impact on the observables. So as I have still a bit more time, I'll talk briefly about what can happen in the core region of the hypermassive neutron star, the Taylor-Spock dynamo. So the idea behind this dynamo is you have some differential rotation and some initial toroidal field that will get sheared into the toroidal field until it becomes so strong that it becomes unstable to some kink-like instability, the Taylor instability. And then some nonlinear effect again will generate the toroidal field again, and that will be sheared again. And this way you have a dynamo loop that can amplify the magnetic field. And it is studied a lot in stellar evolution because it can drive a strong angular momentum in stars, and has been studied for magnetar formation as well more recently. So we did a simple one-zone model for the hypermassive neutron star, where we took the parameters from our simulation at like 7 kilometers inside the core of the hypermassive neutron star, and started with a 10 to the 14 Gauss radial field. And you can see that very quickly, we amplified the magnetic field to some very strong value, more than 10 to the 17 Gauss for the toroidal field, and a few times 10 to the 16 for the radial field. And the dynamo actually stops here when the angular momentum is entirely transported. That means that it could lead to a faster collapse to a black hole, except when you're stable by only solid body rotation. Of course, this depends on some parameter like the initial magnetic field, which is uncertain. What is the large-scale magnetic field right after merger? But if we take some simulation by Aguilera-Miret, we can estimate it to be around 10 to the 14, and that means that this dynamo could happen in a very short time scale, 100 milliseconds. But so we needed to study a bit more in simulation, because in GRMHD simulation, this is very hard to resolve. We need super high resolution, and not enough for now, at least. So what we did is a simple toy model of this dynamo, where again, we started with a 10 to the 14 quadruple magnetic field. And you see the shearing that amplifies the toroidal magnetic field. And then you have the linear part of the instability and the saturation. And this simulation showed that we can reach few times 10 to the 16 Gauss for the toroidal field. And this dynamo also generates, quite interestingly, some strong magnetic field along the polar axis. 10 to the 16 Gauss for the toroidal field. But it raises a lot of questions. Does this field stay confined inside the remnant? Can it reach the surface where it could impact and propagate some matter and drive some jets as well? But overall, with this kind of simulation, shows that the angular momentum, if we take into account the Gauss phase, would be transported in around 100 milliseconds as well. meaning that we would have a dichotomy quite fast between a black hole, if you needed differential rotation to be stable, to have a hypermassive neutron star, or supermassive neutron star, which is stable by a solid body rotation. There will be, for this kind of magnetars, there will be a talk by Clara in a few days. And it also raises question about the impact on gravitational wave, because we have strong turbulence in a very high density region. So is there some modes that are excited and that can emit gravitational wave? Can it have some impact on the F mode of the post-merger signal? And the lifetime as well, since it can shorten the lifetime, could impact some stochastic gravitational wave background detectable by the Einstein telescope. And I don't know, I think I'll leave you with the conclusion that we need to learn more about these MHD processes, because they can impact a lot of aspects of binary neutron star merger.
Alexis?
Thank you. Very, very nice work. I have, I guess, two questions. So one is going back to this nice pointing flux slide that you showed with these overtones, basically, of the alpha omega dynamo, right? It's very interesting. So we see something very similar. So this region of 12, 13 kilometers, where basically in this other part of the hypermassive neutron star, where the MRI really amplifies the magnetic fields. So do you have a sense how actually these large-scale poloidal and toroidal fields emanate from that region? So I agree. We see all the nice diagnostics of alpha omega dynamo and so on and so forth, but in this very thin layer of the star, how do you actually get these large scale fields out into a jet? So something I'm wondering about. I have no answer to.
I mean, it's not clear. One part is the propagation of the magnetic field to the turbulence as well, because there's some accretion, but the turbulence also, you have some dynamo coefficient that are responsible for propagation of the magnetic field as well. And those seems to, at least in the local simulation that we have, seems to drive the magnetic field radially as well. And this could propagate it towards the pole. But I agree with you, the exact interaction on the polar, on how this magnetic field that you are creating in this direction interact with the jet is not so clear for me as well.
Okay, great, thanks. And the other question, so you also showed this very nice work on the Taylor-Sprout dynamo, and you had this simulation in this onion shell ring, right? So something I never really understood here on the Taylor-Sprout dynamo is I always thought that, and you were alluding to this earlier in the overview slide. It's really a global axial modes that get unstable, so these kink modes and so on and so forth. And so you're excising basically here part of the axes. So I was wondering, what are actually the modes that you're exciting in this in the simulation, and how you get the amplification.
Yeah. So here, since we're taking this rotational profile, so this is also why we excite some part in the center. I mean, it's simpler for numerical reasons as well. But this part is more or less in solid body rotation, meaning that's not where you would have this strong axial modes for the toroidal magnetic field. It will be really in the region from 5 to 10 kilometers apart from the axis. But even with that, so the toroidal field is initially very strong. So in this region, where the differential rotation is the strongest, but then the instability makes it happen as well on the poles and everywhere in the simulation. But yeah, initially I agree with you that the modes are mainly localized. So in the equatorial plane, and this is also what is usually found in GRMHD simulation, like this kind of ring at 5, 10 kilometers.
Right. Okay, thank you.
Another question?
Hi, thanks for the nice talk. Do you keep track of the quadrupolar, of the mass quadrupole moment of the object as it evolves? Because with
No,
these strong magnetic fields,
I don't think we take track of it.
you don't compute it. It might be, is it
It-
simple for you to do? You've got
Depend-
the density profile.
Yeah, we have the density, so it should be doable,
Okay.
yes.
We can talk.
Mhm.
Thank you. So let's thanks again, Alexis, and all the speakers of this first part of the session. So now is a coffee break, I think, for 30 minutes. Enjoy.